Okay. Hi, my name is Angela Duran, and this is our MXCT 375 final project.
Hi, my name's Aaron Moy.
My name is Alfonso Navarro.
And my name is Scott Rowland.
This is our MXCT 375 project. Subjects include electromechanical and Arduino code. Within the electromechanical, we have 3-floor elevator activated by push buttons at each level to indicate the desired floor level that the platform needs to travel to. The DC motor is voltage controlled, which can change speed and directions and stop at desired floor destination. 3 IR sensors indicate when the platform has reached to its desired floor location to stop the DC motor at that location. Within our Arduino code applied to gather input on desired floor selection based on push buttons. It stops running DC motor when the desired floor level is reached. Within the Arduino code, inputs are interpreted from the push buttons as well as the IR sensors in order to determine the direction that the platform must travel. The IR sensors determine the position of the platform, and the push buttons determine where the platform is desired to be traveled to. Once the position is determined from the IR sensors and levels is desired from the push buttons, the direction of the DC motor is found by subtracting the level desired by the current position, and this indicates the direction of the motor to travel upward or downward. The code to run the DC motor will stay in the loop until IR sensors on the level desired detects the platform. The electrical parts that consisted within our circuit are Arduino Nano, DC motor, IR sensors, push buttons, the H bridge, and resistors. Push buttons send input signals to Arduino to indicate the desired floor level. Both the push buttons and IR sensors are pull up, meaning that when it's pushed or something is detected, it sends a low signal. DC motors provided power from the Arduino depending on push button inputs, and the H bridge has external 3 volts power supplied to it.
So for the mechanical construction and modification, the elevator shaft itself, the frame and the mass was 3D printed, utilizing a STL that was then modified in Fusion 360 to allocate for the unique functionality of our project. The mechanical system itself involves a pulley system that connects a spool and a shaft, an axial shaft, which will then do translational motion to the mass vertically. So there will be a rotational motion that the DC motor will implement based on the inputs, counterclockwise or clockwise, depending on the input, of course, which then will either extend or retract the rope and the mass being pulled. So it does that translational motion within that vertical axis. There is also potential damping coefficient due to the guard and railing system of the elevator mass itself, to prevent any kind of loose or faulty motion that could essentially hinder some of the inputs from the sensory. So that railing system does have a potential damping coefficient to it. And that's kind of the essential mechanical component. This here is a slide essentially dedicated to the prototyping. In the second image to the left, that is the Fusion 360 STL file with all modifications and elevator mass, including all the guardrails implemented and T-card fins to ensure stability when going through that vertical translation motion. To the right of that is just the same STL file within the 3D viewer model to implement of what it will look like in real life. And on the far right is the splice within the Cura software for 3D printing. And on the far left goes back to the official prototype that is utilized for the Relevator.
So for the electromechanical integration and test analysis, consists of the Arduino assisted through the peripherals for full functionality, where the RR sensors are adjusted to ensure that the platform will stop at the desired level accordingly. Functionality of the push buttons are tested to make sure that it behaves properly. This comes with the pull-up resistor configuration on the Arduino board. And we have to integrate also that the fact that the IR sensors are active low. And then also the axle and pulley system verified through multiple tests, which much custom work had to be done to the final product before it was full functioning due to I guess planned for circumstances.
The procedure section of this presentation primarily centers around the integration of all these separate components, as well as the construction of each individual component. So for the final assembly, we integrated the Arduino code, which controlled the logic for the Relevator, and the Arduino received inputs from the IR sensors and the push buttons, as previously mentioned. This would be turned into an output for the DC motor, thus activating the pulley system, which raised or lowered the elevator platform. And the elevator platform knew when to stop by triggering a new IR sensor, which ultimately allowed the elevator to move to fixed positions and over fixed distances. Aside from that, all of these components were mounted to the 3D printed components to make everything one cohesive assembly and to make the resulting product look a bit cleaner and more accurately resemble a real elevator. We didn't have an external shell or shaft to encase everything because we needed to analyze each of the different components and get pictures, obviously, but ultimately it's a decently realistic physical model of an elevator that would be used in, for instance, the ZAC building. Once we had finished with the physical model and combining all the necessary components, we simulated the same system through MATLAB and Simulink, and thankfully we produced very similar graphs to what we had gotten from our measured data. As you can see here on the different circuit boards, we have the Arduino connected to all of our inputs and our outputs. Over to the right of the Arduino board, it's just a positive and negative terminal that was taken from a separate breadboard, and that's how we connected all our IR sensors, both to the frame of the 3D printed shaft, as well as back to the breadboard without making things too messy. And then over on that same breadboard that houses the Arduino, we have the push buttons. And obviously all the wires are connected in order to send the inputs to the proper pins on the Arduino to ultimately allow the Arduino to then send the signal to the DC motor. Over on this side is where we have the DC motor, and that's connected through an H-bridge, and it's also connected to a power supply to ensure the proper functionality and controls for the motor. For the actual 3D printed components, outside of the frame, we have the elevator platform, which is connected to the string and the shaft extension for the DC motor, which completes the pulley system and allows the shaft to move up and down whenever the motor is activated.
The work distribution entailed essentially all of us working together on multiple components. And some of us kind of concentrated within certain portions of the entire process. So Aaron did the mechanical functionality, construction and hardware installation, and Alfonso did the coding and algorithm functionality. I myself did a lot of the CAD designing and the MATLAB simulation, as well as the 3D printing. And Scott did his contributions to the coding and MATLAB simulation as well. But ultimately, we all had our hands in the melting pot and multitudes of the project.
Here is our demo video showing the physical model for the Revelator work. As you can clearly see, the elevator moves up and down between each of the floors, depending on which button is pressed. So it can go either from the first floor all the way to the third and vice versa, or it can move up or down by just one individual floor. Thus, meaning that each component of the project was successful, and when fully assembled, the entire Revelator was a success. And while there were some issues, mostly in terms of getting all of the dimensions and the components correctly configured, and we did have some issues with modeling every single one of the inconsistencies of the physical model within our Simulink simulation. The most notable example being how when the elevator occasionally catches on the rails, because it was kind of a fringe situation, we weren't able to accurately model that. However, were able to model the friction of the rails on the platform itself using a damper. And aside from those slight issues, the project went smoothly overall, and the team was very happy with the final design and the results that it produced.